we discussed about the four varieties or four forms of Fourier series representation. Okay. So, that means if there is a single periodic function of say time, then in four ways we can represent that thing as infinite series. Okay. Two of them were in complex and two of them were in real numbers. So, like that, and we also discussed about what are the advantages and why and how to correlate their coefficients with respect to the physical situation and how things should be converted from one to the other. All those things we discussed in the previous. We also told that in this segment we will be discussing the same Fourier series concept, but from the perspective of time frequency analysis. That means at the beginning when I started the segment 1, in fact this unit's first segment, I said that everything, all this full course we will be talking either in terms of time domain or in frequency domain. So, now we are in a situation where we can actually talk about those things in much more detailed way. So, that is what we are going to do in this segment. So, for that what we will do is, for example, we will take a signal in say time, okay, but whatever we are discussing now or we are going to discuss now is not restricted to time as independent variable. That independent variable could be even space variable. Okay. Something is changing with respect to space periodically, the same concept will be applied, but we will take our independent variable as time, because for us in this course time will be the independent variable, and that is how the time frequency terminology is coming. Otherwise it should have been space frequency. Okay. Anyways, so for us the independent variable will be time, and what we will do is, let us say we have say a signal which is say I draw a function of time, okay, and this side I am drawing say time axis. Fine. So, this side is time axis, and I have a function of time which is periodic in time. Say I will draw, say this is one time period and this is another time period. Okay. So, this is say t naught, this is 2 t naught, etc. So, t naught is our time period, and let me try to draw a function which is periodic in this. Say I should have okay, and then the same thing I will try to draw, but yeah, whatever. Just assume that they are the same repeated function. So, whatever is there in this segment between 0 to t naught and t naught to 2 t naught, also the same function is there. Okay. Though they do not look very similar, but please assume that. Okay. Now, if such a function exists, then our Fourier series tells us that it can be split into various sinusoidal functions of periods which are either same as this t naught or half of t naught or 1/3 of t naught, like that. That means the frequency which corresponds to those sinusoids will be integral multiple of the frequency of this. That means for that, let us say we draw say the frequency axis on this side. Okay, I will say omega axis, which I will say the frequency. Okay. Now, if we try to plot the components of the Fourier series expansion. So, let me write also the Fourier series expansion for say this ft. Suppose ft we had what, say a, or I will write the other form, now you are comfortable with all the forms. So, let me write this form. cosine of n omega naught t minus phi n. Okay, so this form I am and then summation, I always keep forgetting the summation sign. Okay, let me do one thing. Will it work? I'll shift these things a bit. Yep, and then I'll put a summation sign here. Okay, and n is equal to 0 to infinity. So now let's start, suppose assume that a naught is 0, that means there is no DC value for the function, just for simplicity. And then what do you mean by say n is equal to 1 to plot that? Now when n is equal to 1, so we should plot at omega naught. Let's say omega naught is somewhere here. So this is the point omega naught. So here it will be 2 omega naught, and say here it's 3 omega naught, etc. So here it's 4 omega naught, and like that. Now at every such location, if we draw say a time axis like that, okay, if I draw a time axis like that, and let me also draw the periods corresponding to them, okay, then what this equation tells you, for say t n equal to 1, suppose it's a cos function, let me draw a cos function whose period is this much, okay, say like that. So yeah, so if I draw a vertical, so it will end here, and this is again it's coming like that, so like that. So this is my first function, say a1 cos of omega naught t, and say phi is 0 in this case. I have drawn as if the cos function started at that location, and this height is a1. And now suppose I try to draw the second one, I will draw it here corresponding to 2 omega naught, and let us say its amplitude is slightly less than a1, and it is shifted by say 90 degree or something, and it becomes a cos. Let me draw in some other color. Yeah, so it becomes a sine 1, and that means the phi is such that it has become a sine function, and this has become like this. And similarly, if I go to third one, maybe this has become again something like this, something like that. And if I go to say fourth one, maybe again it has become something like that. So these are sinusoidal functions at every integral multiple of omega naught, okay, 1 omega naught, 2 omega naught, like that, and everyone has got their own amplitudes. And if you sum them up, if you just sum all these functions, then basically you will get this, right? So that is what is the meaning of this Fourier series representation of that function. And when we talk about time frequency analysis, so there are two viewpoints of drawing also. Let's say if I look from this side far away in the omega axis, what I will see is just the time function, isn't it? So let me draw there. So this is say f of t, this is t, and I'll just see the time function just like that, right, which is periodic in time. But then so this, and then the omega axis actually is coming out here, out from the blackboard towards the viewers. And the same thing, if I turn this picture, if I turned it this way, that is looking from top, I'll move it clockwise so that I'm looking from far away in time, then these things, they will look something like this. This is the f of t, and this side is the omega axis, and your time axis is coming out like this. Okay, time is coming up, and here at say at omega naught you will see a cos function like that. So this is that function with a1 amplitude. Similarly, this one you will see as a a2 amplitude. So this is with a2, and similarly at here a3, again suppose here this is a3, and here it's say a4. So these are the sine functions or the shifted cosine functions. Okay, I'll say that these are the functions which you are looking at, and the amplitude is here. Okay, you are looking at them from this side, and that is the meaning of, so this is in a way the frequency domain representation, and this is the time domain representation of the same function. So that's how we generally look at them. And then when you when somebody tells you that, okay, how do you think in terms in the time domain? Okay, so let's take the example of the same simple case, the spring and mass. It's a spring and there is a mass, and you are applying say f of t. When you think in time domain, basically what you are doing is you are applying a force, which is ft, which varies with time like this, and then you are trying to or somebody is asking you how the response of the system will be when the force is like that. Okay, then when you think in terms of frequency domain, what you are actually should be thinking is split this force into its harmonics, okay, or the sinusoidal components, and then apply individual these harmonic functions as excitations. And we discussed in a previous segment that harmonic is a simpler version of excitation than a periodic one. Okay, remember the natural vibration, the harmonic and the periodic, and then it will come to a periodic. So now a periodic thing, we shifted it to or simplified it to just a harmonic excitation, and now it's always simpler to know that, okay, if this harmonic excitation is applied to this system, how the system will behave. So same thing you do with this. Suppose this harmonic excitation is used, how the system will behave. Only thing is that this phase also needs to be considered here. Okay, so then, and once you get the answer with all these split questions and all the answers you sum up, and then you will get the answer to the question that if I apply this time function, what will be my output. So that's how you actually solve a problem or thinking in terms of time and frequency domain. So that's the basic idea behind splitting a time function into frequency or combining frequency domain thought process into time domain. So that's what I wanted to just discuss so that it will be clearer about when you write these equations of Fourier series, all the four forms, what exactly you should be visualizing in terms of time and frequency representation. In fact, there are much even a better representation which will in fact lead to a better way of understanding when we go to the aperiodic excitation, because when the excitation becomes aperiodic, things will become slightly more complex, and we will once we go there we will discuss about that. For now we can stop it here with this visualization of the Fourier series representation or the time frequency representation for a periodic time signal. So see you in the next segment.